The third example is a little bit, trickier or harder. Let's see. But again, just need more work. It's not that hard. So what we have here, again, a circuit which has an input at the gate and the output is at the drain. So it is also a common source amplifier. Now we have a load. So the other two circuits doesn't have loads. RD was a load. Here we have a load RL. And of course that will reduce the voltage gain, as we will see. Just like the effect of our load on BJT amplifiers. So let's see. So the transistor here has a V threshold equal to 1.5 and Kn is equal to 0.25 milliampere volts squared. Find AV, R input and R out. Again, we're going to start by the DC analysis. So in the DC analysis, we're going to remove all the AC sources and the capacitors. So we're going to end up with this circuit here. RG, 10 mega ohms. Here is VDD, which is 15. Here is RD, 10 kilo ohms. Okay. Here is IG here is equal to 0. And what is IG? IG is equal to VD minus VG over RG. Since it's equal to 0, so from that, VD must be equal to VG. So VD is equal to RG, VG. Since VD is equal to VG, so VDS must equal to VGS. We just added minus VS here and minus VS here, so we didn't do anything. So VDS must be larger than VGS minus V threshold. So we are working in saturation. If two numbers is equal to, let's do that in another, just to clarify it. If you have 2 equal to 2, so basically 2 is must be larger than 2 minus something, for example, minus 1. Okay. What is ID? So let's calculate it. So ID equal to Kn over 2. VGS minus V threshold. VGS is how much? I think it's not known. Yeah, it's not known. We're going to deduce it. So this is VGS minus V threshold, which is, I think, 1.5 square. And the ID is also equal to, from that, this is VDS. So from that outer loop here, you have VDD equal to VDS plus ID RD. So you can say that ID is equal to VDD minus VDS over RD. Which is basically 1.5 minus 0.1 VDS. So 1.5 minus 0.1 VDS equal to 0.125, which is 2.25 over 2. VGS square. 1.5 square would be VGS, or 1.5 square. This would be plus minus 3 VGS. Okay, remember that VGS is equal to VDS, so this is equal also 1.5 minus 0.1 VGS. Now it's one unknown here, so in that part the unknown is VGS, in that part also the unknown is VGS. So this will give us two solutions. The first one is VDS or VGS equal to 4.41, and the second solution, VDS or VGS, both are the same, okay, minus 2.21. So this is, of course, rejected because it's a negative. VDS cannot be negative while the transistor is on. And this will be accepted. Okay. We can calculate current now. ID is equal to 0.25 over 2, 4.41 minus 1.5 squared. This will give us 1.6 milliamperes. We can calculate also GM. GM is equal to Kn VGS minus V threshold. So this is 2.4 and VGS is 4.41 minus 1.5. So GM will be equal to 0.73 milli ohm minus 1. Good. So the AC part number 2, the AC analysis. Okay. First is the equivalent circuit. So let's first draw the circuit by canceling the DC sources and shorting the capacitors. So we're gonna have our load here. The capacitor is short. Then we're gonna have RD with ground. Source is also ground. Then we have this resistance RG. Then we have the capacitor is short. Then V input. I'm gonna draw the equivalent circuit of the transistor and connect the rest. So GM VGS. And here is the gate, here is the drain, here is the source, and here is VGS between these 2 points. Then I'm going to continue. Between the gate and the ground is V input. Between the gate and the drains, there is a resistor RD, which is a new thing here. And that's what makes the analysis a little bit difficult. We finished by the gate, now the drain connections. Between the drain and the ground, there is RD. And remember, the source is grounded. And here is RD. And also between the drain and the ground, there is RL. And here is VO. Okay? Good. Let's start by the AV, which is VO over V input. Good. Let's assume this current is I input. So we have two basic equations here. This node here has a voltage equal to VO, and this node has a voltage equal to V input. So I input equal to V input minus VO over RD. This point is V input, this point is V output, and this is RD. This is number one. Another equation here is the voltage of VO. So this I input come here and has two branches. One component to go to that branch and another component with VGS GM. So I input is equal to first current is GM VGS. And the second current, which goes in here, equal to the voltage across these two resistors over the parallel or divided by the parallel combination of these two resistors. So it's equal to VO over RD parallel RL. I will call R D parallel RL. I will call it R. Okay. So from that, VO is equal to I input minus GM VGS multiplied by R. And R again is RD parallel RL. This is number 2. I will put now 1 and 2. So I will remove I input and put this value. So VO. So let's write this clearly. And this is number 2. Substitute. Then substitute 1 and 2. So remove I input and put Vn minus VO over RD. So VO is equal to R V input minus V output over RD minus GM VGS R. And remember V input here. This is V input. V input is just equal to VGS. So we can remove any and put the other. So let's remove VGS and put V input. Just to make us more consistent. So VGS equal to V input. Okay. Good. Remember, EV is VO over V input. So I will divide both terms, or all the terms by V input. So if we divide by V input, I'm going to get here EV equal to R over RD. And here is, let's first combine. Yeah, let's combine VO on one side and all the other stuff on the other side, and then divide by V input. So VO, then 1 plus. From here, we're gonna get R over RD equal to V input and R over RD minus GM R. Then we can divide now by V input. So VO over V input, which is EV, equal to R over RD minus GM R over 1 plus R over RD. We can take minus GMR as a common factor, minus GM R, and remember R is RD parallel RL. And this will give us here 1 minus 1 over GM RG. Oh, I'm sorry. This is guy RG, not RD. I am very sorry here. Oh, this is RG. This is this resistor here, RG. Okay, so this will miss many things here. So what else should be changed? Yeah, this should be RG, not RD. So this will be also RG, not RD. Yeah, this should be RG. What else? Yeah, any RD will be RG. Yeah. Okay, yeah. That's it. So it is RG, RG. Okay, so this is RG here, and 1 plus R over RG. Let's write it R over RG. One note here is this term is approximately 1. Let's see why. First, 1 over GM RG, it's 1 over 0.73 multiplied by 10 mega ohm. So it's just 1 over 7.3 million. So this is basically much less than 1. Okay. And R over RG, remember R is RL parallel RD. RG is 10 mega ohm. RL is 10 kilo and RD is 10 kilo, so the combination is 5 kilo. Okay. And this is 10 to the power 7. So this is again much less than 1. Okay. So AV is approximately equal to minus GM R, which is RD parallel RL. You can of course do it. It will be, you know, it will be just 1. 1 minus 0.000001, you know, it's 1 out of million, okay? Which is 1. It's 0.9999. And again for the denominator. So it will be again 1.00000, you know. So it's just 1. So AV is what would be AV? Yeah, 0.73 multiplied by 5 kilo ohms. Remember, this is milli ohm minus 1. So that's why I keep it all the time in milli, because I will multiply it by something in kilo. So kilo will be cancelled by milli. So this will be at the end how much? Minus 3.75. Okay, this is number 1. Let's have another. Okay. Now, number 2, our input. Okay, so our input is also complicated, but we're gonna do it. So we have, let's draw the circuit again. Okay, our input basically is V input over I input. Okay. Remember, V output is AV, V input, and from the Kirchhoff here, from that big loop, we will find that V input equal to the voltage across RG plus VO. So this is basically equal, V out is equal to V input minus the voltage drop across RG, which is I input RG. So let's divide both by I input. So AV, V input over I input equal to V input over I input minus RG. What is V input over I input? It is R input. So AV, R input. Remember, we know AV minus GMR, RD parallel RL equal to R input minus RG. So from that, our input AV minus 1 equal to minus RG. So our input equal to RG over 1 minus AV. Okay, so our input equal to RG over 1 minus, here is minus GM R, which is RD parallel RL. Okay, so this is basically RG over 1 plus GM RD parallel RL. And we're going to calculate its value. It will be 2.1 mega ohm. Very big as usual. Number 3, RO. For RO, we're going to cancel the input and replace our input, RL, I'm sorry, by VXIX. So from that same circuit, so let's copy and paste. So we're going to remove RL. And the input will be just short. And we're going to put VXIX. This will be shorted. So basically VGS is 0 now. So VGS is 0 because this is the gate, this is the source. They are both connected to each other. So VG minus VS is 0. And RO is VX over IX. When VGS equal to 0, this means that GM VGS is also equal to 0. So this is open circuit. So this circuit will be reduced to the following. VX IX RD, and here is RG. So VX over IX is basically RD parallel RG. Of course, the 10 kilo ohms, the parallel 10 mega ohms is just 10 kilo ohms. Don't try it, okay? It will be 9.9999 kilos, so it's 10. So this will be approximately equal to RD, which is 10 kilo ohms. Okay, guys, so this is basically the common source amplifiers, okay? It has, moderate to low amplification gain. It has very good input resistance. It has moderate to high output resistance, okay? So it beats common emitter if we compare it to common emitter, because it's, it's analogous to common emitter. It beats it in the R input. Same R output, but it has less, we can say less, but we can manage that. I mean, we can play with RD, but as we see, most of the time, it's a very low value. Okay. We also try to put RS, and again, it was similar to the degenerate resistance RE in common emitter amplifiers. It also reduces the gain. Okay. But makes EV less sensitive to GM, if we assume that GM is sensitive to heat or something. Okay. Okay, guys, so thank you very much. And next time we're gonna explore another type of, or another configuration, which is the common gate and also common drain. So stay tuned. Have a good day. Bye-bye.